I will.
Okay, can you see my screen?
Yes.
Okay, I shall go for it. So the talk is as advertised on geometry, symmetry, and higher dimensions. I'm going to start with some basics of fundamental physics before I get on to what my own research is about. So start with the question: what is a fundamental particle? In physics, a fundamental particle is seen as an excitation of a field. So, for example, the electron is seen as an excitation of the electron field, the quark as an excitation of the quark field, photon, the particle of light, as an excitation of the electromagnetic field, and so forth. Which begs the question, what is a field? A field is a mathematical quantity which varies over a set of coordinates. And here we've got an example. This is average temperature across the United States. You can see it's got a north-south axis and an east-west axis. So this is a two-dimensional field, a field that ranges over two coordinates. We can think of a field as inhabiting a space on which we can define transformations. So, for example, if you have a two-dimensional space, one such transformation is a two-dimensional rotation, or in 3 dimensions, you can have a 3-dimensional rotation. Fundamental fields such as the electron field and quark field we were looking at both vary both with the space coordinates and with time. So if you were looking at three dimensions of space, you've got 3 space coordinates usually labeled X, Y, and Z, and time labeled T. These fields can be classified according to how they transform under the 3-dimensional rotations using a quantity called spin. And again, we've got some examples here. The Higgs boson, famously discovered a few years ago at CERN, is an excitation of the Higgs field, which is a spin 0 field. The electron field and the quark field are excitations of spin half fields, and the electromagnetic field is an excitation of a spin 1 field. A symmetry is a transformation under which something stays the same. So, for example, the value of a spin 0 field, which is known as a scalar field, at any given point doesn't change under rotation. So if we were to think of, for example, the temperature at New York, you can rotate your map and the value of that will stay the same. Whereas the direction of a spin 1 field, a vector field, changes under a transformation. So this is a map of wind direction, wind velocity across the Earth. If we take a particular wind vector and we were to rotate the map, the direction the arrows pointing in would change. So now we go on to gravity. Gravity is viewed in general relativity as a curvature of 4-dimensional space-time with the 3 coordinates of space and 1 of time, a curvature caused by masses. So this diagram basically shows you a star which warps space and time around it. So the light from a distant star travels not on a straight line, but on a curved line following that curvature of the space. And gravity is associated with space-time transformations. For example, the rotations we were looking at just now, or boosts or stretches. A boost is basically where you have two reference frames moving with respect to each other. So that's moving from, for example, my point of view to the point of view of somebody driving or running past me at a fixed speed with respect to me. I've looked at these space-time transformations, analysed them in a paper called Tangent Space Symmetries in General Relativity and Teleparallelism, which has recently been published online. if you want to find it, you can just do an internet search for that phrase, and it should bring up the online version, which I'm afraid is behind a paywall, and my own version, which is the preprint, which is on my ResearchGate page. But do contact me if you want a link for either of those. So that's gravity. There are other fundamental interactions: the electromagnetic interaction, and that we've already mentioned, and what's known as the weak interaction, which is responsible for radioactive beta decay, and also plays a role in nuclear fusion and particular types of supernovae. Those two have been combined into something that's known as the electroweak interaction, described by the electroweak theory, which predicted extra new particles which were found in CERN in the early 80s, and it uses the Higgs mechanism, which involves the Higgs boson that's also recently discovered at CERN. And the final known fundamental interaction is the strong interaction, which is responsible for binding quarks together into protons and neutrons. All of these non-gravitational interactions are associated with symmetry transformations of spin half fields, which are known as internal symmetry transformations. We can then ask the question, can we view these internal symmetries as space-time symmetries? And the answer is yes, according to Kaluza-Klein theories, developed by Kaluza and Klein. These add a spatial dimension, so you've got 5 in total, and use the equations of general relativity. And if you do that, you find you end up with the equations of electromagnetism coming out of it. Klein suggested that this extra dimension is rolled up to a subatomic size, so we don't see it. In fact, it's very, very much smaller than a nuclear size, so it's just not possible to see it directly at all. These higher dimensional theories were developed in the 1970s and 80s, and their symmetry properties are examined in papers of that period. My research is along these lines. I take a very high density vector field on a higher dimensional space. The high density causes a huge curvature, which wraps up the extra dimensions to these subatomic sizes. And the geometric structure of the universe is like a tube of varying radius. So essentially, if this y mu is representing our usual 4 dimensions of space and 3 dimensions of space and 1 of time, then there are extra dimensions running perpendicular to it, orthogonal to it, which take form a compact space, a closed space, that where the curvature varies from one point in space to another. So in some places more compact, in other places it's less compact. And the spin half fields we were talking about, the matter fields like electrons and quarks, can be combined to make spin 1 fields. And then the variation in the radius of the tube that I was talking about, this change in the curvature, are the non-gravitational interactions with these spin 1 fields made from the spin half fields. So that's what my research is about in outline. If you want to read more about it at about the same level, but filling in a lot of the gaps, you can find it at my website, warpedandbroken.com, particularly on the pages warping and breaking. So that covers my my research.